If you have seen all the lectures and probably done all the assignments, I'll just go through some of the basic questions so that you can make sure you can understand whatever you. It's like reinforcing whatever you've learned, and also it'll make it easier for you guys to answer the questions. So first, let me share my screen. Okay, is my screen visible? Are you able to see my screen? Where you can see a word file. Are you guys able to see my screen? If I open this word file, can you see? Okay, so if you're able to see my word file, then let's get started. So first, I think, see, guys, if you type in, it'll be difficult for me. If you can just answer, you can unmute yourself and answer the questions. That'll be much better, and we can cover things quickly. And also, I would know that you guys are there. Otherwise, I'll be teaching to nobody. Okay, is it okay? Can I hear a yes from you? Yeah, yeah, sure. You can ask your doubts. You can in between also, so that's fine. So anyway, so first things first, you might have understood the different types of systems, which is like the first thing that you're taught in thermodynamics. So I mean, I have few questions. You can just answer me. So as you can see here, I have a system where there's neither heat nor matter is transferred across the boundary. So what kind of system is that? Yeah, yeah, you're correct. So basically, it's isolated system, and that's what. So that's the correct answer actually. So what is an open type of system where you can have both heat and matter, or energy and matter can be transferred across the boundary? And what is a closed system? Just give me a minute. Talking with somebody. Yeah. What is a closed kind? What's a closed system? Yeah. Where you have both. Where you have what? Okay. In closed system is energy exchanged. Guys, please, if you can answer, it'll be like much better. In closed system, which is exchanged, energy or matter? Yeah, of course. So in closed system, energy is exchanged, but matter is not exchanged. So that is quite obvious. So now we come to the next kind of system where we have next. Basically, we have different laws of thermodynamics. In this week, the only zeroth law was covered. So basically, what does zeroth law state? Does it have to do anything with conversion of mass and energy? Okay, so if you see here, zeroth law states that if system A and B are in equilibrium with each other, and then there is system A and C that are in equilibrium with each other, then A and B are in equilibrium with each other. Basically, if two systems are in equilibrium with a third system, then they are in thermal equilibrium with each other. So that's what zeroth law tells, and this is quite important because this introduces to us the concept of thermal equilibrium and temperature. All right. So from this, sorry, yeah, let's say we have two systems, and A and B. They are in thermal equilibrium with each other. Okay, and then we also have A and C that are in thermal equilibrium with each other. So now zeroth law tells that B and C are also in thermal equilibrium with each other. Okay, so in class and generally people explain it using this. Let's say you take a thermometer. Generally, we have mercury thermometer. So let's say you keep mercury thermometer at in a particular liquid, and the temperature turns out to be, let's say, 30 degrees. And then you say you keep the same thermometer in some other liquid, and that also is in 30 degrees Celsius. So we can say that first liquid and second liquid are in thermal equilibrium with each other because they have the same temperature. Did you understand? Yeah. Okay. Just a moment. I will have to admit somebody. I'll have to automate this. I don't know why. Okay. Yeah. So this is important because this introduces the concept of temperature. So then, using the concept of temperature, we can measure many other extensive properties and intensive properties that will come to later. So now, the next question is kinetic theory of gases assumes that the collision between the molecules are perfectly elastic, inelastic, partly elastic, or does not care at all. What is the main assumption of kinetic theory of gases? Yeah. So they do collide and they do not interact with each other, but when they collide, it's just perfectly elastic collision. Okay. So that concept you guys are clear with. So now we have again we any thermodynamic property, it can be an extensive or intensive property. So now give me an example of extensive property. So what is an extensive property? What decides whether it is an extensive or intensive? Yeah. So basically, extensive properties depend on the amount of matter that is being present there. So now is pressure an extensive property? Is pressure an extensive property? Does it depend upon the amount of matter? No, okay. So then what? Give me an example of extensive property. So this is no. So that we are quite clear with. So this is no. But what are the examples of extensive property? Yeah, mass, volume, then yeah, internal energy. So what is pressure then? Okay, so then pressure is an intensive property. So now it's an intensive property. Any other intensive property? Yes, temperature, density. Good. Okay. So now you have some idea. Now then, this is quite an easy question. So we have two glasses of water. One is 350 Kelvin and another is a 330 Kelvin. Now you mix both glasses, and at equilibrium, once they equilibrate, what will be the temperature? Yes. Can you guess tell? You have two glasses of water which have equal volume. One is a 350, one is a 330, and you mix them. At equilibrium, what will be the temperature? Just give me a minute. Yeah. Yes. What do you guys think? Which one? Is it 300 Kelvin? Obviously not. One of these two. Which one? Which one do you think? It's quite easy. Come on. Ideally, when you mix two liquids or two solids, when you bring them together, it depends on the material properties or the mass of the solution, mass of the system, basically. But here it does not depend because we know that it is water, so same material property. It is the same volume, 500 ml, so we don't have to worry about the mass also. It's just the temperature. One is 350, other is 330. Now, it's just going to be the average, right? So 340 Kelvin is going to be the answer. So now we'll come to the next question. So some of the questions following this, these are the ones that were in practice assignments. So now whatever questions that I'm going to talk about, like another four questions, all of them will help you to solve these assignments and also drive in the concepts related to molecular velocities. So now, first question is, let's say we have a box filled with nitrogen gas at a certain temperature T. So the question is, will all the particles or all the molecules in that box have the same velocity? What do you think? In class, in the lectures, sir taught a certain velocity called RMS velocity. Do you remember that? This is RMS velocity by 2. Do you remember this? Do you remember this, guys? Okay, so now let's say, can you answer this question then? Will all the velocities be the same at a given temperature? Let's say we have a box filled with nitrogen gas. Let's say there are Avogadro number of molecules in that. Will all the Avogadro number of molecules have the same velocity or different velocity? Okay. Can you just type in your answer also? Just tell me yes or no in the chat box. Let's see. Will they have the same velocity or a different velocity? Yes. Okay. So now Hershey has told that she will have different velocities, which is indeed the correct answer, because we are going to get a distribution of velocity over here. At any given temperature, all the molecules will not have the same velocity. Okay, so we'll get a distribution of velocity, and that is given by Boltzmann distribution, which is basically okay. So this complicated looking function is quite simple actually. You just have a Gaussian like distribution, but not exactly Gaussian. If you see the if you see the distribution actually, okay, just give me a minute. I'm using this for the first time. I'm having difficulty in drawing lines. Okay, if we see here, if you see the velocity distribution, it will be something like this with a longish tail. Okay, so you have different types of velocities over here. Let's say this is a probability distribution f of v, and this is the velocity. Okay, now you have certain points here, which is this is the maximum point. So because of that, this value over here will be your maximum probable velocity. And then you have two other velocities. One is RMS velocity and another is average velocity. So now let's figure out which one is RMS and which one is out of these. Okay, we have two lines here, average and RMS. We'll figure out whether RMS will be greater than average or average will be greater than RMS. We'll do this by deriving the formula for each of them. Again, this will be helpful for your assignments. So now, again, I'll rewrite the Boltzmann distribution over here, which will be helpful for us. By So all these are constants. Okay, whatever you see here, they're all constants. Okay, so now, can any of you tell how can we derive this? So let's say first we'll go for root mean square velocity. Okay. Velocity. Okay. Can you tell me how we can derive this? Okay, you take take a box of gas, and what do you think is the internal energy of the system? Since they are not colliding, since the gas particles are not colliding in a dilute gas, in an ideal gas, we we assume that they do not collide with each other. Sorry, they have elastic collision and they do not have any interaction energy with each other. Therefore, you will not have any potential energy. So the internal energy, which I'll write it as U, which we know is the sum of kinetic energy plus potential energy. Here it's going to be zero. Therefore, it's just going to be the kinetic energy part. So, what is the kinetic energy now of all the particles if you take? It is the average kinetic energy of all the particles, right? You have particle average. So, you take average here. So, this is going to be your internal energy. From kinetic theory of gases, we also know that internal energy is also equal to 3 by 2 kBT, or we can tell 3 by 2 RT. So here I'll use kBT because we are considering only the molecules. So now we can equate these two. Are you people following this up to this? Yeah. So just I'm just doing rearranging after this. 3 kBT by M. All right. So now this is squared mean velocity. Okay, this squared mean velocity. But then we do not get much meaning from squared mean velocity. What will we get? So the idea here is we have to take a root of this. So when you take a root of this, basically it looks like this. 1 by 2 is equal to a root over 3 kVt by m. So now this is the formula for root mean squared velocity at the molecular level. Let's say we are considering at molar level. Okay, I have to admit somebody. Yeah. Let's say we consider things at molar level. So then all that we have to do is multiply this numerator and denominator by Na. Okay, so we know kBt into Na is equal to, what is that? What do you get there? What do you get when you multiply Avogadro number with Boltzmann constant? Come on. Anybody? We get the universal gas constant. Okay. Similarly, this is the molecular mass multiplied by your Na is going to give you the molar mass. Alright. So now when we substitute this, instead of writing as one root, I'll just write RMS. RMS. Okay. Or rather, I'll just write it like this. VRMS is enough, more than enough. VRMS, therefore, is equal to 3 RT by M. Okay. So this is an important result. that we'll keep for some further problems later. All right. This is the first time I'm using this. A little trouble. Okay. So now we have one of the velocities, that is root mean square velocity. So what are the other two types of velocity? Can anybody tell? Please let me know if you're not following anything. Sorry? Yeah, average velocity. So now, how do we get average velocity? Yes, average velocity, you're right. So now, how do we get average velocity? Okay, how do you get average velocity? You have a distribution, probability distribution. And so let's say you have any probability distribution. Okay, let's say this is just P of X. Okay, that's a probability distribution. So how do you get average velocity from that? Average of this probability distribution. X bar is equal to integral over all values x p of x dx. Okay, so this is how we get average of any given probability distribution. Now, as we know, we do have a probability distribution with us for the velocities, which is the Boltzmann distribution. All right. So now I'll maybe write out the Boltzmann distribution once again. So you do see that it's quite important. All right. So now we have the most Boltzmann distribution. Now what we need is average velocity. Okay. So now how do we do this? Integrate over all possible values, which is 0 to infinity. Okay. So now we have this v and then f of v, which is the velocity distribution, integrated over dv. So this is what we'll have to do. Okay. Now let's say what I'll do is, if you see this function, if you see this function over here, we have all these things, 4 pi m, 2 pi kpt, 3 by 2, all these are just basically constants. So I'll directly take them out as the first step itself, so that we save some steps, which is basically 4 pi m, 2 pi kbt, 3 by 2. We have 0 to infinity. We have v already there, and from this we have dot v square e power minus m v square by 2 kt, 2 kbt. Okay, so we have this now. Okay, dv. Now then we can further simplify this. So what I'll do is I will name this constant. Okay, let me just continue using that. V cube e power minus m by 2 kbt v square dv. So now this is what we have right now. Okay, so if you see this one, this integral, This is a type of integral that is, this is like, it is given by this integral, again 0 to infinity. We have, let's say, this is similar to this kind of integral. Okay, minus alpha x square dx. Okay, where is this? So we already have integral tables from which this is an involved derivation, which I will skip. I'll just skip for now. You can see integral tables where you can get the integral for this particular form, and it is a quite simple form where you get just 1 by 2 alpha square. So now in our integral over here, the alpha is m by 2 kbt, minus m by 2 kbt. All right. So that is what we'll be working with. So now if I go to the next page, we'll go to the next page. I think I need more space. Okay. So now we have this. So our velocity average is therefore going to be all these values, 4 pi m by 2 pi kbt 3 by 2. It's going to be just 1 by 2 alpha, where alpha is going to be minus m by 2 kbt. So what I'll do is I will directly multiply that. Okay. So we have 1 by 2, right? Here already 2 is there. So 2. Okay, wait. Maybe little slow. This is alpha squared. So we have minus m by 2 kbt, which is squared. Okay, this is what we have. Now we can start cancelling terms so that things get simplified. So, sorry. Pi m by 3 by 2, and this is going to be root 8, I guess. Root 8. 2 to the power 3 by 2 is basically a root 8. Yeah. Then we have pi 3 by 2. I'm just writing it out like this so that it's easier for simplification. Again 3 by 2. So now this kbt will come up. So this is going to be 4 kbt again squared divided by 2 and m squared. All right. So now you can cancel some terms. 2 is going to be 8 by root 8. I'll just do it. So this is going to be this just it's going to be 1 by pi 1 by 2. Then m is going to be, we have m squared below, so 1 by m 1 by 2. So then we have only kbt left. So kbt 1 by 2. So if we come below, so this is the it's going to be the final equation where we have the root over 8 kbt divided by pi m. So this is another equation. This is the average velocity equation. Again, this is at the molecular level. Let's say we want to tell it at the molar level. What do we do? If we, how do we convert this to molar level? Anybody? We did it last time. Yeah, multiply and divide by Avogadro number. So Kb into Avogadro number is RT, and then small m into Avogadro number is the molar mass, which is capital M. Okay. Now this is our final equation. So this is the average velocity equation now. All right. So again, this was quite simple, right? All we had to do was take the average of a probability distribution. Okay. Is this clear? If you have any doubt, you can ask me, so that you know we're all on the same page. Okay. Now let's go back and revisit our graph. Revisit our graph. Okay, so this is the velocity distribution that I showed, right? So I showed that velocity, maximum probable velocity, is the one where there is the distribution peaks. Okay, so now how do we find this velocity? How can we find this velocity? Can anybody tell? We have the graph, I mean, we have the equation for this distribution. So basically for this line we have this equation. Now how do we find this point? Anybody? How do you find the peak or turning point of a graph? Okay, at this point in the graph, okay, at this point in the graph, what is the slope of the line? Okay, can anybody tell what's the slope here? What is the slope here? Anyone? Let me see how many are behind. Joydeep is there. Joydeep. Okay, one of you tell what is the slope at that place? You can also type in if you don't want to talk. What is the slope at that point? Anyone? Harshi Ammu? At this place, what is the slope? Can you see? It's kind of flat line, right? So what do you think is the slope here of this line at this point? So here the slope is 0 because it's a flat line. Okay. So since the slope is 0, the first derivative of the function at this place is also 0. Do you see that? Because this one, f first derivative is the slope of the line, right? Locally. Do you see that? Okay. So given any line or function, the first derivative gives you the local slope. So since this point, as you can see here, Since this point is the maximum point at the place at which the curve basically turns, that point the slope is going to be 0. So that means first derivative is going to be 0. So using thus that condition, we can actually find the maximum probable velocity, because the velocity there is maximum probable velocity. Okay. So now that's the property that we'll use now. So let's see. Now we'll get the maximum probable velocity. Maximum probable velocity. So first derivative at VMP is going to be 0. So now again we are going to use the Maxwell Boltzmann distribution. Now what I'll do is I'll just l- dump all the constants as certain values. Okay. You see 4 pi by 2 pi kt kbt 3 by 2 e squared e power minus mv squared by 2 kbt. Okay, what I'll do now is, okay, let's find the first derivative here. Let's not simplify too much. Let's find the first derivative, which is equal to 0. So if first derivative is equal to 0, I'm using chain rule now. Okay, because we have one variable here which is v, and again in the exponential we also have v. So first we'll use the chain rule, where I'll differentiate this first, keeping this constant, then we'll keep this constant and do differentiation for this part. Okay, so now we have 4 pi m by 2 pi kbt 3 by 2. So if we differentiate this, what do you get? I'll keep, please tell. I'll just write the constants till then. What is the differentiation of that? V squared? 2v. Okay. So then again we have the same constants again. 4 pi m 2 pi kbt 3 by 2. V squared will remain there. What is the differentiation of this? It is the same. Okay. That's 2 kbt. And then we differentiate this part again, which will give us minus 2mv by 2 kbt. Okay, so now let's simplify a lot of things. Since since this is 0, we can take out all the common variables. So 0 is equal to, so this is common, this part is common, so I'm taking that out. kbt. So what I've done is I've just taken that out. So then I'm also taking this part out, where EMV, that is also again common, mv squared by 2 kbt. So we are left with 2v plus v squared into, let's cancel this, minus mv by kbt. So since all these are common, all of them can go to 0. Okay. Doesn't matter. So now, so therefore we have 2v minus mv cube by kbt is equal to 0. So this is quite simple, right? So now what we can do further is we can also take another v, and then that will also go to 0. So, so now what happens is 2 minus mv squared is equal to kbt is equal to 0. So this is what we have. Okay. Now we have what we can do is we can just take it to one side. kbt is equal to 2. Then if we come down, we have, this is basically the most probable velocity. V squared is equal to 2 kbt by m. So therefore vmp is equal to root over 2 kbt by m. So this is what we have. So this is again at the molecular picture. When you want it at the molar picture, we can multiply and divide by Avogadro number and get the 2RT by capital M equation. All right. Yeah. So these are the three different types of velocity that you can get from the Maxwell-Boltzmann distribution. So now, what I want you to do is, now I will draw the Maxwell-Boltzmann first. I'll write everything. Let's kind of summarize. So we have V RMS, which is equal to a root over, what is the value there? Sorry. 3 RT by M, right? Am I correct? Oh, sorry. And then we have V average, which is 8 RT by M. And then we have V most probable, which is 2 RT by M. Okay, am I correct? I'll just check once. Yeah, yes. Yeah. Okay, we have all these things we have summarized. Now let me draw the graph again, distribution again. We have V over here. We have the probability distribution. So it goes like this. Oh, sorry. We have a longish tail. So now this is straightforward, right? So this point is the VMP. Now, so you see VMP is the smallest value. Can you see that?
Yeah.
Harshi or Jaideep? Can you see that? VMP is the smallest value. Okay. So now, what is 8 by pi?
Oh.
Just do a calculation with phone.
Oh. Oh.
What is 8 by pi? How much is it? 8 divided by pi is 2.546. Okay. So basically, so the second value is going to be the average value. Okay. And the last one, VRMS, is the highest value out of this. So now, can you tell me why V average is lower than V RMS? Can you tell something based on the probability distribution? Can you tell? Okay, in average, what are we doing? So in RMS cap, what are we doing? It is a root mean squared, right? There's something extra we are doing. Here it's only mean. Here we are doing something squaring, right? So basically, since there is a long tail where you have some high velocities over here, when you square them, they become much bigger. Okay, and when you are taking average of those squared values which have a higher value, you are going to get a bigger mean compared to one where you're not squaring at all. In average, you're not squaring at all, but here you're squaring. So these long tail that is present in Boltzmann distribution will lead to higher squared values, which is giving you a higher VRMS compared to V average. So that is the concept behind this. All right. So now we have these three problems. We have these three velocities. You can use this to solve some of your exam assignment problems. I think I've covered most of the assignment problems. I mean the ideas. What I want you to, I'll just show two more examples, which will kind of set you up for all the assignment problems. Okay. So we have these formulas. It's quite straightforward, right? Eighth question. Can you see the eighth question, Harshi? Joydeep? Huh. So can you calculate it? What I mean, you've been listening to the class. Can you calculate it? You have temperature here, and then I've given you the R value. Yeah, I want you to calculate the root mean squared, average, and most probable velocities. Can you calculate and tell me the answer? I will do on the side, but I want you also to do. So tell me the formula for VRMS. Root over. Okay. So now let's work through the problem together. We have R, we have T, and so what is the molecule M for nitrogen gas? Into MS. What is M for N2? Yeah, 28 grams per mole, right? So now we just need to calculate. So 3 into 8.3145 into temperature, which is 298 Kelvin, divided by mass, which is 28. Now I also want you to give the units over here. So which is joules. Joules is basically what? Kg meter square second square. Okay. Kg meter square second square into moles minus 1. Sorry, this is a mistake. It has to be temperature. Okay. Let me just change it. Yeah. Sorry, Kelvin. Yeah. I have Kelvin minus 1. And then for 298, it is going to be Kelvin. And then below we have grams, right? This is grams per mole, which is equal to 28 into 10 power minus 3 kilograms per mole. So we need to add another 10 power minus 3 factor over here. All right. You see that? Now all these within the, okay. Okay. Can cancel this, cancel this. These two guys will go. So now we just need to do some calculations. You can use a calculator to do that. I'm not going to sit and do this. How much is it? 3 into 8.1. Sorry, 3145 into 298. Sorry, 0.028. H to the power 0.5. How much are you getting? 16. 16. Okay, wait. A root, okay. I'm okay. I'm not getting that value actually. Can you do this multiplication? I'm actually getting a value of 515.24 meters squared. Once I take the, sorry, meter per second. Once I calculate the, once I do this calculation. You're not getting this? You take your time. Let's see whether we are getting this. We get, sorry? Ah, okay, fine, good. So then we'll go ahead to, next is average velocity. So what is the formula for average velocity? Which is pi into m. So again, it's a similar calculation. All we need to do is do some multiplication and we can get the value. I have already done it and I get around 474 meter per second. Okay. So I mean you can do for most probable velocity as well. Similarly, all we have to do is MP. I can just do it quickly. It's going to be 2 into 8.1, sorry, 3145 into temperature is 298 divided by m, which is 0.028 to the power 0.5. I'm getting around just, sorry, 2, right? 2 RT by m, getting a value of around 420.69 meter per second. 8. Yeah. All right. So you get the point, right? Like it's quite easy once we have these formulas. And do you appreciate something good here? I mean, to something remarkable with the values? Let's say just take average values. It is 474.7 meter per second at less than room temperature, around room temperature. Do you think this is quite a high speed? Anyone? let's let's consider nitrogen as an ideal gas, and let's say this is what we are observing, and this is quite a, isn't this quite a high temperature? Sorry, high velocity, I mean. Yeah, actually this is quite a high velocity to think about it. Okay, so now this is quite simple. The next one is, again, this is one relation that you will know. Okay, what I want you to calculate is just the RMS velocity of hydrogen molecule. Okay, using this result. I don't want you to calculate, use this formula, but then use this result to calculate the RMS velocity of hydrogen. How can you do that? The relation that we are going to use for that is VRMS. What is VRMS formula? 3 RP by M. So, what is the relation between RMS and mass? Okay, I must add another thing at temperature, at the same temperature. T is equal to 298 Kelvin. So, what relation we can use here? Yeah, how can we use it? Same this formula, but then I don't want to calculate everything. VRMS is proportional to what? Root over 1 by mass, right? So that is the one that we are going to use now. We need, if it's at the same temperature, we can neglect temperature, but then if we consider if we are calculating a different temperature, again we can do it. Okay, so that's the idea over here. So we have VRMS of nitrogen. Okay, VRMS we have for nitrogen, which is, how much is it? Let me go up. Sorry, which is yeah, 515. I'll just keep it as 515 meter per second. Okay. Then we have mass of nitrogen, which is 28 grams per mole. We know the mass of hydrogen molecule, which is 2 grams per mole. What we need here is we need the VRMS of hydrogen at the same temperature. So we can just easily, VRMS nitrogen by VRMS hydrogen is going to be equal to mass of hydrogen divided by mass of nitrogen. So it's as simple as that, which is equal to, which is 2 by 28, and that's 14. So VRMS hydrogen is equal to root over 14 dot VRMS nitrogen. Okay, and that is quite simple. We just need to multiply. So what is that? We have 515 into root over 14, which is 1926 or 1927 approximately, 1927 meter per second. So this is the velocity of hydrogen molecule at room temperature. Again, which is quite high, and it's quite high. Yeah. So as you guys can see, now what I'll do is, are you able to understand all of this till now? Yeah. Sh- Okay. Yeah. No, no. I've just multiplied it directly with VRMS 515. Okay. Yeah, yeah. Okay. Root over 14 into 515. Okay. So that's what I've done here. Okay. You have any other questions? Okay. So in that case, maybe we can, quickly see some of the assignment questions if you would like. If you have any doubt, you can ask me. You see here, we have actually derived the average velocity, root mean square, most probable velocities. We have derived all that. See again, if you see here, these two questions, that you see here are actually concepts of what we have discussed today. You see here the pressure of two cylinders containing same number of helium and xenon gases at same temperature. Okay. Oh, sorry. What have I done? Okay. At same temperature and volume. Okay. So that's what they are asking you, and then questions based on the last question that we just did. And these are like basic questions related to zeroth laws. So I hope you guys will be able to answer all these questions. If you have any doubts, you can ask me now. And I will stop sharing my screen. Yeah. If you have any questions, we can discuss further. Otherwise, we can, stop the meeting. Any further questions? Do you have any questions? I think so. That's what I have prepared for now. I don't have anything else to discuss. Okay, Jaideep, do you have any questions? Okay, all right.